Hi, my name is Samuel Young. I'm I guess almost fourth year student in the Goldsmith Computational Modeling Laboratory at the University of Michigan. Today I wanted to talk a little bit about how you use the MKMCXX microkinetics simulation software package to generate turnover frequency plots. Like the one that you see here in the top middle, this is a plot from our recent Journal of Catalysis paper about platinum ruthenium alloying in the nitrate reduction reaction, electric catalytic nitrate reduction reaction. And this plot was generated using MKMCXX as well as Python and Matplotlib. So I guess just as an overview, I want to sort of go over what MKMCXX is and sort of how its input files are organized, what data you can expect to get out of it, and then also go through how you use a small Python interface that I have started writing in order to automate doing a lot of these calculations in a high throughput scheme. Okay, so what is MKMCXX? So it's basically an ODE integrator written in C++ that's specifically geared towards doing mean field microkinetic simulation, especially for reactions that happen on catalyst surfaces. So it is free to use, but the author has chosen to make it closed source, and so you need to, there's basically binaries released for Debian and for Windows, which you can download free, but you're not going to be able to sort of compile this or alter the source code. So the way you get it is you just go to this website here, mkmcxx.nl, and you can download those binaries for free. I've also created Docker images that are sort of just wrapped in Ubuntu base images. If you need to run these on a computing cluster where there's incompatibilities to different versions of libraries it's compiled against. So I know in particular on NERSC Cori, if you want to run the latest version 2.15.3, it's compiled against a newer version of the glibc library than Cori has. And so you'll need to use a Docker image through Shifter in order to use it. But if you do that, it works fine. And this link right here, I'll just show you where this is. So you can go get those. If you just go to my page on Docker Hub, you can see that I have two tags here for MKMCXX. There's 2.7.0 and 2.15.3. And so feel free to get those. I guess the images could be smaller if I based it on Alpine or something, but because it was compiled on Debian, I felt that Ubuntu was just the safest bet to get binary compatibility. Okay, so let's now talk sort of about what MKMCXX does. Basically, you give it an input file, which is traditionally called input.mkm, and you give it sort of four sections of data, four sections in this file. You talk about the compounds that you're going to be using, the reactions that are involved in the mechanism, if you want to perform different runs of this reaction mechanism at different temperatures, for example, to do Arrhenius plot generation, and then just a multitude of different settings that you can use. I do want to say I'm not a pro at this. I can just sort of share what I've learned through my use of it, but there's a lot of information available. There's not really a lot of tutorials and guidance, but the ones that are given are sort of good enough to get you started. And of course, there's a large reference for different keyword settings that you can use. So basically, I think what I'll do is I'll just propose a simple reaction mechanism. I'll show you how you can create this file manually, and then I'll show you a demo in Python with a Jupyter notebook. So let's just consider just a simple reaction mechanism. So it's simple enough to run on our computers here. That's just basically a reversible isomerization of two species that exist on the surface, right? And so you have adsorption-desorption steps for the reactant and the product, and then of course a surface reaction step in the middle right here. All right, so you have 5 species if you include all the starred variants, right? Because sites participate in the reaction, and you have starred variants of A and B that are different. And so you can basically what MKMCXX does is it sets up this system of ordinary differential equations, and then of course you give it initial conditions like the initial concentration of free species or the initial coverage of the surface bound species, and it basically integrates these forward in time with some preconditioning and other things that help it converge better, and then it gives you sort of what the steady state converged coverages and free species concentrations would be. Okay, so now let's go and make our own MKMCXX input file just using a text editor, and I'll show you how you can do that. Okay, so let me actually go out and get MKMCXX and just put it someplace where I can run it. So you can just go to the MKMCXX website. It looks like this, and you can go to the download links. And again, here are the Windows and Debian versions. So Debian, that should work against any, a recent version of Ubuntu. And then Windows 10 is supported, and I think Windows 8 as well. So I'm on Linux, so I'll just get the Debian version of it. Hopefully it'll work. I'll download it to my downloads folder. It happens pretty quick. Right, so here's the MKMCXX binary, and if you just run it, you can see it will give you usage. Usually the way that you call this is just MKMCXX-I and then your file name, which is usually input.mkm. So I'm going to just quickly add this to my path. I have to really install this properly, but just for now, I'll quickly add this to the path so that I can just use it in the terminal. Okay, so that should work now, so let me just try navigating away. Okay, so that looks like that worked. Now, when you're making a new file, often the easiest way is just to go to the wiki, and then you can look under the wiki, you can see tutorial examples. So not the tutorial videos on the homepage, but just tutorial examples, and it gives you sort of the sample input.mkm file. And so you can see, hashes denote comments, and then you have these 4 sections. So you have compounds, and then you have reactions, and then you have settings, and then you have runs like that. And so often you can just sort of copy this and sort of just put it in. Okay, so yeah, so we'll just start the file. We'll just start it with a compound section. I guess I can just put a comment at the top. Let me just enable highlighting. There we go. So we can just put a comment at the top. Test simulation MKMCXX file. Right, and so you see sort of the way the compounds are defined. It's basically the semicolon delimited file. So for compounds, you first have the name of the compound, which is just a string. It can be anything. Well, maybe not anything, but it's just a string that uniquely identifies that compound, whether or not it's a surface or species in the initial concentration. So this is actually almost sort of set up a little bit, like our simplified reaction mechanism. So I'll just sort of change these things. So A and B are free species. That's good. We should have a lot of A, not any B because that's a product. A star, B star, and star are site species. So that's good. I'm going to start off actually with none of the adsorbed stuff because I want to model the adsorption, and of course 100% coverage of the sites. So we'll do that, and then we'll go to our next section, reactions. And so this is good. This is set up the way I would set it up. So 2 Hertz-Knudsen reactions to model the adsorption-desorption. These are a little bit misaligned. Let me see if I can just fix this. Okay, there we go. Yeah, so this is a little bit better. So basically, same sort of thing, first column of this semicolon delimited thing for Hertz-Knudsen reactions is the type of reaction, and then you can do AR for Arrhenius reactions. And then the second column is sort of what the products and the reactants look like. And so you just write out in curly brackets name of compound plus name of another compound, and you can put coefficients in front if you have more than one of them. And then of course this arrow, and then the product side of the reaction. And then for Hertz-Knudsen reactions, you specify sort of all these Hertz-Knudsen parameters that you would have. Let's see if I can line that up a little bit. Okay, so this is better. Right, so you have an area parameter, molar mass, a K-factor, sigma factor, like that, sticking coefficient, and adsorption energies. So I'm going to actually just change these to a few different values so that it will sort of match what we do later in Python. Again, so, not super realistic, these parameters, but it'll help get the point across to make the TOF plot. And then also just, if you wanted to do DRC analysis, you then have to add an additional column. And then also if you have a Arrhenius reaction, same idea, but just the parameters a little bit different. So let me try and line this up a little bit. Okay, that's a little bit better. So same idea, except this time you're just specifying the forward and backward pre-exponential factors and the forward and backward barriers. So let me, of course, just change these values again to be a little closer to what we wanted. And then, of course, we'll specify, if we were going to do DRC analysis, to include this reaction in it as well. And so you see sort of what I've set up here. is just a case where what I'm trying to do is sort of make it so that the adsorption and desorptions are very fast, and then the surface reaction is the one that's limiting. Or specifically that, you have the surface reaction that can go forward, but it's a little bit less reversible. Okay, and then the next section is the settings section, and so we're going to do a sequence run simulation, which is where you can basically do this analysis at different temperatures. If this is a gas phase reaction, you could specify the total pressure in bars. I'm going to just accept the default value, which I think is just 1 bar, because I really want to model it more as sort of an aqueous phase reaction. And then there's, of course, there are different settings that you can use. One that's really useful is this one called use timestamp. Make it 0. And what's going to happen is that when it writes the results into an output folder, when you run the simulation, it will try and timestamp that folder, like make the folder name a timestamp, and that's tough because if you want to get back into a lot of simulations, all the folders are going to have different names. So if you make it 0, then it'll just call a folder run, which is nicer. Okay, and then also if you're doing reaction order analysis or DRC analysis, you need to specify the reagents and the key components. So I'll just have it be all the all the things that's not just a site. So reagents equals A star, B star, B, like that. And then sort of the same thing for key components. Okay, and then you can turn on reaction order analysis and DRC analysis by just setting those parameters to 1. And if you wanted, you could have debug equals 1 to get more debug information. Okay, and then finally the run section, this shows all the different sequence runs you want to do, so the different temperatures. And then this time here, this is an integration time, so how far out do you want the ODE integration to go? And then you can also specify absolute and relative tolerances as sort of convergence criteria for the coverages and concentrations that are being integrated. You can, like it says in the note here, you can omit these 2 columns and just set a default value in the settings. So yeah, you can do that. I'll just leave it as it is for just now. And I think for now, I actually want to start at 300 Kelvin and go up to just 900. So I'll just set that to be 300 and get rid of all of the rest. And then the integration time, I want that to be just uniformly 10 to the 12th seconds for all of them. And then I'll just keep the absolute and relative tolerances. So this should be everything you need, I think, to do the simulation. We have our 4 sections specified. And yeah, I think those are the right initial concentrations. So now we'll just exit and we'll actually run MKMCXX on it. So I've temporarily put it on my path, so I should be able to just do MKMCXX-I input.mkm. And you can see now it's doing the analysis, and you can see this output here where it did all the sequence runs, the DRC runs, and things like that. And what it's now going to do is create a whole bunch of different output files that you can then view. Right, so let's take a look at this folder. So here's that test sim folder that we had, and inside you can see there's our input.mkm file with some output logs, and then this run folder, that's where all the simulation results are. So you can see there's a lot of different things that you can look at. So we did sequence runs at different temperatures, and you can look at the files for a certain temperature. And what this contains is you would then look at, for example, sort of like the integration results throughout time of each of the different species coverages and compositions. And you can start to see where it starts off and then it, converges very, very quickly all throughout like that. And then derivatives just shows you the time derivative with respect to the time step here of each of those. And that can be useful for approximating rates. So you have that for all the temperatures. And then you have range, which is sort of the steady state results for all the different sequence runs that you did. So now if we open up coverage here, you can just see it's the steady state coverages and concentrations of each species at a different temperature. And the same thing for derivatives. K constants, you can calculate those. So for example, for the Hertz-Knudsen reaction, those are calculated from the different Hertz-Knudsen parameters. And then let me see, for the Arrhenius reaction, that should just be, okay, yeah, so these are the full rate constants. And then if you look at the prefactors, you can see we have our Hertz-Knudsen reactions, and then of course the Arrhenius reaction where the pre-exponential factors were just constant for all the different cases. You can look at rates of different reactions, and then you can of course look at equilibrium rates for different equilibrated reactions. And then, of course, you have rates, and then it also just calculates the base 10 log of the rate as well for you. So this is interesting. I'm not sure why those didn't converge, but you can sort of see, you can sort of pull this data, as a data frame or whatever you want in order to make plots. You can also, it also does make plots for you. So you can get a lot of plots like your coverage plots here, derivatives. So like this would be production or consumption of different species. You could look at reaction orders. It's funny, I don't know why it's not there, but or just rates of reaction like that. So that's really useful as well. And then of course temperatures. It will then plot, of course, all of the convergence data as it integrates through time. Another interesting thing it makes, and by the way, these graphs, you can turn on the generation of these graphs. You can turn it off if you don't need them. I don't really find a need to produce them because you can always just plot them in Matplotlib if you want, but it's there if you want. And then of course you have network plots right here. So these are GraphViz files. So if I just make another terminal right here, let's take the 500K one. I can just do this. So .t PDF. I'll just take the 500K one. It'll generate a PDF file. And then if you look at that, you can see it generates this nice little graph of, I think these are like initial concentrations or maybe steady state concentrations, as well as sort of the fluxes of species. So that's nice for visualizing as well. So that's sort of just a quick overview of the different results that you can get, the different kind of results files that you can get. And you would then use this to, either in a script, or you could read this from a folder, or you could plot different things if you wanted to. And that's how you sort of make a simulation just by hand in a text file. So we've just seen how you can create an MKMCXX simulation using a text editor, and how you can just run it and look at the results yourself. I've also started writing basically a Python interface, a Python module that lets you automate that process, at least for mostly basic simulations. There's a lot of features that MKMCXX lets you do, like different things with plotting and graphs, and lets you simulate plug flow reactors. So it's definitely not feature complete and definitely not mature. Definitely will welcome any pull requests that you have or suggestions for improvements. So right now I've created this Git repository that just shows where you can get the sort of the files for this tutorial. Let's go back to the web browser. So here it is right here. And here's a notebook, and then here's the MKMCXX Python interface, this module right here. And this sort of allows you to define many of the same things like compounds and reactions and settings that you would do in a text file. And so the idea is that once you have it in Python, you can then use the power of Python scripting to automate the process of doing many of these simulations at once, which is what you need to do in order to create a turnover frequency or DRC plot. Okay, so I think now let's go to the Jupyter notebook, and I'll show you, so that notebook in the GitHub repository, I'll sort of walk through that step by step, and show you how you can create the turnover frequency plot. Okay, so let's take a look at this demo notebook. This will sort of just walk through how you can set up an MKMCXX simulation using the Python interface, and then also how you can make the turnover frequency plot. So we'll just import some packages right here. You can get rid of these magics if you don't like them. Utility functions for pickling and unpickling data, and just some plot settings. Okay, so just like before when we were defining an MKMCXX simulation file, you have your sections of the input file. You have your compounds, reactions, runs, and settings sections. So we'll sort of replicate that here. So there are classes in MKMCXX to help you define a compound. Just the same way. You give it a name, a string name, you tell it if it's a site or not, and then you can set different settings for the initial concentrations and whether to include it in TDRC analysis. I find it easiest just to key them all in a dictionary by the string names. And then you can then go on and define reactions. And the same thing, there are two classes for reactions, Hertz-Knudsen reactions and the Arrhenius reactions. And so basically the way that these classes work, or the way that this works, is you just specify what would be on both sides of the reaction. And so you have one A species adding with one site species going to one A star species, right? So these are the stoichiometric coefficients. And then of course you have different Hertz-Knudsen equation parameters like the area, the atomic mass, your sticking coefficient, and so on. And then of course every reaction you can specify whether to include it in degree of rate control analysis or not. And similarly, there are similar parameters for the Arrhenius reactions, except you're just specifying the forward and backward pre-exponential factors and your forward and backward barriers. And so, yeah, so the species, you can define them here. I just put them in a dictionary because it's easier to reference them. And then the reactions should just be a list of reaction objects that reference those species objects or these compound objects. Right, okay, so now we're going to define the settings and the runs, so the last two sections that you need to make an input file. And so the settings, you just make them into a dictionary. You can have string parameters like this, you can have float parameters. If you're doing DRC analysis and you need a list of species, you can just put them in a list and we'll automatically format them correctly with curly brackets surrounding each species name. And there are a lot of different parameters. You should look up on this link right here. This tells you a lot more about the different kinds of parameters you can use. Not all of them are supported by the Python interface yet, sort of just basically what you'd be able to put into, this sort of 4-section input file. But a good number of them are. And then also what runs you want to have. So we basically just implemented that same simple reaction system I showed in the PowerPoint with this reversible isomerization A star going to B star. And we've implemented the reactions that would model the adsorption-desorption of A and B, as well as the reversible surface reaction as an Arrhenius reaction. And then we want to run this at different temperatures, and so we're going to set the type to sequence run, and then we'll specify the different temperatures that we want. And the way that we do that is we make a list of dictionaries that are keyed like this, where you have the temperature in Kelvin, and then the integration time in seconds. Right, so I guess I'll just go through some of these parameters. Absolute and relative tolerance, those are the tolerances that it uses to determine when it's converged. And then, of course, for each sequence run, you can specify the maximum integration time that you want. Right, so if it doesn't converge within that time, it'll just stop, in this case, at 10 to the 12 seconds. Reagents and key components, you need these. You need to specify those in order to calculate reaction order analysis, to calculate effective or apparent activation energy analysis, and of course DRC and TDRC analysis. You can specify whether to turn on those analyses or not. You can also just specify whether it produces the plots or not. That's an issue in the older version of MKMCXX 2.7.0. Sometimes it freezes because it can't generate all the plots, and you don't need them anyway. You can just plot them with matplotlib, so you can often just turn that off. Debug, whether you want to include additional debug information in the output logs. So now that we've defined that, we've defined our species, our compounds, our reactions, our settings, and our runs. Now we'll put it all together into a microkinetic simulation object that looks like this. And it just takes basically those parameters, reaction settings, and runs. Note that you don't actually have to specify the compounds because it will just pick those up from the reactions. So I guess you don't really even need to make the species dictionary. You could just specify compounds like that. It's just easier to do it this way, I think, though. Okay, so you'll set up this microkinetic simulations object, and you want to give a name for the directory where it should write the input files and where it should run MKMCXX. And so, of course, if you're doing a lot of different simulations, you just want to make sure that that directory name is unique from all the other simulations. So in this case, I'll just call it test sim. So you can see there's no directory here. And then when you actually want to run the simulation object, so this microkinetic simulation object has a run method, and that will cause it to write out the input.mkm file to the directory and call MKMCXX on it. As you can see here, there's also a write input files. I've tried to design it to work a little bit sort of like ASC calculators, file calculators. But in this case, if you call run, it'll call the write input files first. And so you'll say sim.run or microkinetic simulation.run. In this case, I'm specifying a custom path to MKMCXX because I haven't installed the binary on my path yet. As long as the MKMCXX binary is on your path somewhere, you can just ignore this. You don't have to specify it. I'm just doing it for my system here. So let's actually run this, define the species, define the reactions, define the settings, create the simulation object, and now we'll actually run it. And of course, you could print the standard out if you wanted. And you can see sort of the same output that you would have had before. And so this looks like it was successful. It looks like it converged. And so you have additional debug output. So you can use that. We'll just get rid of that for now. And then after you do that, you can run the read results method of the microkinetic simulation object, and that will then go into the directory, so you can see it's right here. You have your input.mkm file. You have the run folder that has all the different results for all those temperatures we had, as well as range results. So just sort of the typical things that you would get from an MKMCXX run. And so read results will go down into those directories and basically collect as much of the data as it can, and it will make them into basically a big dictionary of data frames. And so if we look at results, we can sort of inspect that and see the way it looks. Right, so that's in the range results folder, and you have the different sort of data files, and these are data frames. They're just printed like this. I acknowledge this is probably not the cleanest way to do it. Really, these should be sort of property attributes of the results object. So that's definitely an area for improvement. But even as it is right now, it makes it very easy to sort of access, any particular part of the data that you want from that simulation. And so, for example, we could then go in and pull out from the range results the actual rates, and we could pull out the rate for the rates for this specific reaction right here and plot them. So you can see for this adsorption reaction, you can see that as the temperature increases, the rate of that reaction goes down. And then we could do the same thing for looking at the rates of the surface isomerization and its inverse reaction. As you can see that the forward isomerization is faster, but they both get lower as temperature gets higher. And so that's a way that you can sort of quickly pull out data and plot it. So what I've just shown you is for this single simulation, and of course that, just like an ASC calculator object, you specify the parameters you want. It wrote out this folder, it wrote out the input file, it ran the program on it, and then it recovered the results. And so that's sort of the utility of this class, is that it lets you prepare these simulations very quickly and very easily without having to write the files yourself. Okay, so now let's go and take a look at actually creating a turnover frequency plot. And so that just involves running many of these simulations at the same time. So we'll go down to this section now. So yeah, let's say that now A and B are intermediates in a reaction mechanism. They're not really and again, this is a toy system, so maybe not bearing the most resemblance to reality, but just pretend that they're intermediates in a reaction mechanism where you've found from DFT analysis or from literature that there are thermodynamic descriptors for the activity and absorption energies, and that those thermodynamic descriptors are oxygen and nitrogen binding energies. So we'll call those EO and EN. And of course, the applied potential matters as well, because now we're going to pretend that we're doing electrochemistry. Okay, so now all the barriers of the surface reactions, the Arrhenius reactions, and the adsorption energies of the Hertz-Knudsen reactions, those are going to change as a function of those descriptors. And so the idea now is, of course, when you construct a turnover frequency plot, often you're plotting as a two-dimensional function of two descriptors. And so the idea is you want to create this plot and sort of map over what the behavior of a turnover frequency or of a particular rate in the mechanism, how that changes as a function of the descriptors. And so the way that you do that is now, instead of just making a set of reactions, a list of reactions like we did before, we're now going to generate those dynamically as a function of the descriptors. So we'll just define our species the same way as we did before. And now we have this function, so instead of just making a list of reactions, it will now make that as a function of oxygen and nitrogen binding energies in the applied potential. And so you can see here before, where we just had a constant for the adsorption energy in this Hertz-Knudsen reaction, now it's whatever a linear scaling relationship we discovered. And the same thing for this Hertz-Knudsen reaction, and the same thing for these forward and backward barriers. And so I've added sort of an IPY widgets visualization so that you can just see for yourself, here's the generated reaction list as you would normally have it. But now as you move these oxygen and nitrogen binding energy sliders, you can see that those adsorption energies and these barriers will go and change, and they'll also change as a function of the applied potential. Right. So the idea now is that, like I said, you'll create this range of energies. So here I've put this, I think it's, minus 100 to it'll be 0 kilojoules per mole. And that will be the range for sort of both the oxygen and nitrogen binding energy. So we'll sort of create this grid of points where now we have oxygen and nitrogen binding energy varying over that range, minus 100 to 0 kilojoules per mole. So we'll make those grid points, and you can just plot them and see. So this is what your turnover frequency map would look like. And the idea is that now we're going to run a separate microkinetic simulation at each one of these points, and then pull out the rate of a reaction at each of those points and make a contour map on it based on it. But of course, there's a problem, because if you go back up here, you'll notice that there are some combinations of oxygen-nitrogen binding energies in the applied potential that produce like negative Arrhenius barriers, and that's unphysical. And so we don't want to consider those points because we can't depend on the results that we get from the microkinetic simulation, and we don't even know if they'll converge. And so what we want to do is, out of all these points, we want to filter out any of these points representing a pair of oxygen and nitrogen binding energies that would lead to a negative Arrhenius barrier anywhere in the mechanism. I forgot to mention, by the way, we're assuming just this fixed applied potential, 0.05 volts versus SHE. Right, and so we have all these points, the grid points here, and it's just a list of these oxygen-nitrogen binding energy pairs. So we'll just define a filter function that goes through the mechanism for each pair of oxygen and nitrogen binding energies and test to see if there's any negative barriers anywhere. And so we can do that, and we can just filter them in this way. And what we find is that if we actually plot the remaining points, now you see that a little less than half of those points are gone. So that's great, because that's about a little less than half of the simulations that we now don't have to do. And if you look here, there's this sort of linear function, and that of course represents where the sort of the lines where the barriers would be zero. And so anything above that line we're going to consider. So there's sort of lines right here, and then if you notice, it's also cut off this point up here. Right, so we're sort of limiting ourselves just to this region right here. And so now for each of those points that's left over, or for each pair of oxygen and nitrogen binding energies that's left over, we now want to assemble that set of reactions for each of those pairs of oxygen and nitrogen binding energies. And so I'll just do that right here using a list comprehension. And the way I'm organizing this is that it's often helpful to just track all the metadata as you go along. So each reaction set in this list of reaction sets will be a dictionary that's keyed with the oxygen and nitrogen binding energies and the applied potentials. And then of course the corresponding set of reactions with the correct barriers and absorption energies for those thermodynamic descriptor values. So I'll generate that list right here. And what we can see is that if you just inspect the first element of the list, you can take a look and see how those energies differ. Right? So for example, here's the first one. And you can see it's got a particular barrier and it's got particular absorption energies there. And then of course we can just look at a different one. Let's look at number 55. Or 56, I guess. And you can see that the barriers are different now, right? So we now have all those different sets of reactions that we can use. And so then what we're going to do is just go and, again, define our settings and runs. And then we're just going to create a whole bunch of different microkinetic simulation objects, one for each set of reactions. Okay, so we'll define our settings. They're just about the same as before. And in this time, instead of analyzing things at different temperatures, we're just going to look at everything at just ambient temperature. Standard conditions about. And so sort of the same thing now. So now instead of just one microkinetic simulation, you're going to have a whole bunch of them. And again, I choose to organize this just by making a list of dictionaries that are keyed with the metadata representing our thermodynamic descriptor values. And then of course a simulation object where, just as before, I give it the reaction set for that particular set of thermodynamic descriptor values, and then the same settings, and then the same runs across all the simulations. And then, of course, because we want the directory names to be unique for each simulation, the easiest way is just to put the thermodynamic descriptor values in the directory name. So we're going to now set up all those simulations, and then you can just take care of this. You can run these using some sort of multi-processing or parallel arrangement. So we're in a Jupyter notebook, and the easiest way is just to use like a multi-processing pool. So I have a worker function. So again, simulations is now this list of dictionaries that has a microkinetic simulation object inside of it. So the worker function is just going to take each one of these dictionaries, look inside to get the simulation object, call the run method. Again, this is just for my system. You can leave that argument out if you have MKMCXX on your path. So it's going to run the simulation, which is going to write out the files to the correctly named directory. And then we're going to go and store in the results key the results of that simulation using the read results method. And then just return that back. And then you can just use a multi-processing pool IMAP operation to sort of complete all of that. And so we'll do that here. And it's simple enough that this can just run on your computer. Of course, with more complex mechanisms, you'll want to run this on a supercomputing cluster. And so instead of 6 of these, you'd run maybe 68 of these processes on a KNL node. But for now, that's done. And then I'll just, I'll take this results list here. By the way, let's just inspect that and just see what that looks like. So we have results, and now we can just look at the first one. So it looks the same as before. It has all the information that we passed it, the microkinetic simulation object. And then it also has, oh gosh, where is it? Yeah, and then it has this results key. So all the different results that you would get, and you can sort of dive into those and pick out the value that you want. And of course, if we go to number 56, you can see it's different, right? And then I'll just cache this to a file so that if I was working on it in a cluster, I can just download this file and continue the analysis on my local computer. So I'll load it in. And then the idea is now that so let's say that we want to make a turnover frequency plot. So this is, the barriers and the absorption energy specified make it very likely that the surface reaction will be rate limiting. So let's just look at the turnover frequency sort of with respect to, just this reaction right here. And so in this case, we would just be interested in looking at maybe like the log 10 rate of this forward reaction rate, this forward isomerization. And so the idea is that, again, results item is a whole list of results, whole list of dictionaries. And each of those dictionaries has a results key. And then you can dive further down into that and pick out the exact parameter that you want, which we do right here. And so basically for every one of these, we want to sort of just, pick out that parameter and then return it along with the metadata into the simplified results. And we can, just do a map operation to get those and then convert them into a data frame. So now if we take a look at what the simplified results look like, now you can see this is very useful. So now we have each pair of oxygen and nitrogen binding energies. And then we have this, I guess this should really be rate log, right? But yeah, the log 10 rate of the, of that A star going to B star isomerization step. And this is in the perfect form for us to now make a contour plot. And so you can just use matplotlib's try_contour_f or try_contour functions and, feed it these functions, and it will create a plot for you that looks like this. And so again, just because of the way the numbers worked out, this is probably not physically realistic, but you can see the point. We have sort of the same shape region that we had with those points, with the grid points I showed you earlier. And here we can see it's very clear now that as you move towards more negative oxygen binding energies and more positive nitrogen binding energies, the rate of the reaction will go up. So this TOF would go up. So of course you would need to figure out sort of which reaction to use, and so again you would have to decide for your particular system what you're interested in plotting. But you can, basically all I've done, right, is just gone into the results and I picked out this particular result across all the different simulations and I'm just plotting it. So you can do this for turnover frequency plots, you can do this for selectivity charts, you can do this for degree of rate control factors that are calculated. You can make DRC plots. So there are all sorts of things you can do, but really just what this Python interface does is just automates the process of creating MKMCXX simulation directories and reading the results and aggregating them so that you can then easily make this plot. So I hope that sort of covers how you use the Python interface. Again, feel free to go and hack on the MKMCXX class, submit pull requests if you like. This notebook again is up on the Jupyter. It's up on our GitHub repository, so you can go and play with it. And yeah, that's basically what we did to make the plots in our recent journal of catalysis paper. And you can then plot other things on top of it, make legends and whatever you want to do.